All right, welcome back. When we last left off, we were all buzzing about secant slopes, average rates of change, the difference quotient. All of those things are basically synonymous. This was the problem that we were looking at. It was an application problem about a population of fruit flies, and the idea was that if I wanted to know how fast this population was growing at day 23, that is a weird idea that you've never seen before in algebra, because algebra can't deal with that kind of question. Okay, and we'll talk about why here in a second. We can't really find it directly, but what we did, and you did this on problem 7 and 8 last night, is we found some secant slopes. We found some average rates of change between, say, these 2 points, and then these 2 points, and then these 2 points. So we just kind of pushed the points closer, and we found that the slopes were converging towards a specific value. That was really the discussion we had at the end of the last example problem yesterday. So really, we're just still finding slope, all right? I mean, this right here, y minus y over x minus x, is just slope. It's really what it is. Now, today, we're going to do something that algebra could never do, and that is to find the rate of change on a specific day at a specific point. Very, very beyond the realms of algebra. And this is the slope we're looking for. We call that a tangent line, okay? What we found yesterday is that as we pushed this point back, the secants, these 2-point lines, got closer and closer to our 1-point line. That red one is really, really close. The concept here is, could I push that point all the way back to the line itself? And the answer in algebra is a resounding no. We cannot do that. Once again, secants hit 2 points. Tangents hit 1 point. That's the one I wouldn't necessarily give to you yesterday. Tangent lines in geometry are lines that intersect a circle at 1 point. Tangent lines in higher level mathematics are lines that intersect a curve at a single point. All right, same idea, 1 point of intersection. The blue, green, purple, and red lines all have 2 points of intersection. That allows us to find the slope, because as we were doing yesterday, slope is y minus y over x minus x. We know how to do that. What we can't do with a single point is do that relation, and that's what I have highlighted here as you read this. The problem is that we know only 1 point. Our usual definition of slope requires 2. All right. How can you possibly do y minus y over x minus x if you only have 1 y and 1 x? This is the exact same information you're going to find in your course pack, but I gave you a slightly new picture. And then what I did is I took the fruit fly aspect of it out and put it in generic terms. So this is at the bottom of your 2.4 worksheet packet, whatever you want to call it. It explains the same information. I just played around, I reworded it a little bit. Notice in red here, the problem is that we only have 1 point. Our algebraic definition of slope requires 2. You can't find the change, the rate of change between 2 points if you only have 1 point. So this is where a dude named Pierre from French, and he was more of a mathematician by hobby. His official thing was he was a lawyer, and kind of a big time lawyer within the government monarchy system at the time. And he came up with this idea which he called the dynamic approach to tangency. And so I have it written here, probably worded just slightly differently than it is in your course pack here. But this is what we're going to walk through right now. So here we go. Step one. Start with what you can calculate. What can I find? Well, I can find slope anytime I have 2 points. And so that's why we start with a secant line, okay? Any point really works, but why would I pick a point like way the heck, out here, right? Might as well pick a point that's somewhat near to begin with. That's step one, pretty simple. Find a slope. Find a slope you know you can find. Step two, we find the limiting value of the secant slope if it exists. Now, that's a fancy way of saying that we push the point back toward the tangent slope. We push the points back. We push the x values back, back, back until they get closer and closer and hopefully infinitesimally close to that tangent line. See how these distances that they are away on the x-axis keep getting smaller and smaller. And while we do that, the slopes of these lines seem to be getting closer to the slope which intersects the curve at only one point. We call that the tangent line, and we're looking for the tangent slope. If I could just keep pushing those points back into that point, right, into that point, we should be able to force our lines into a tangent line, or our slopes into a tangent slope. And that's what step three is. We define the slope of the curve at point P, at the point, to be this number, the limiting value of those slopes. And so once again, going back to step two, I know this sounds really mathy, the limiting value of the secant slope, but what that basically says is we're going to take the limit of the secant slopes. S what, right? You guys now know a little bit about limits, but what are we going to do with that S? And that's where this little picture in your notes comes in, okay? So this is just a generic situation where we have 2 points, A and B, which creates points A, F of A, and B, F of B. Hopefully, that seems really familiar to you because that's the average rate of change that we found yesterday, right? The average rate of change, which we came up with yesterday, was F of B minus F of A over B minus A, Y minus Y over X minus X. I guess I could go ahead and write it down. It looks like I did F of A minus F of B over A minus B, but we certainly agree it's the same thing. So what are we going to do now? Well, we are going to, first of all, change the way that we're talking about this. Yesterday, I gave you a way of rewriting this that we call the difference quotient. And all I really did is I said, you know what, instead of calling this point right here B, I'm going to define the distance between the points as H. Some textbooks use delta X or delta A or whatever. Delta X would be a change in X's, but I'd say more than not, they use H for that distance. And so now I can rewrite B in terms of A. It cuts down on the number of variables in this expression. So B becomes A, which is how far we started away from 0, plus the value H, which is how far we've moved. So B becomes A plus H, which means that my point, I'm not going to call it BF of B anymore. I'm going to call it A plus H F of A plus H. And you guys saw this yesterday, and then we subtract the points, right? I plug in the new Y values and the new X values. I probably should have done F of B minus F of A so that this, otherwise I think I would get negatives and have to cancel the negatives, but this is the way we did it yesterday. And so this is the way that we definitely want it to look. And then we found, right, we found that on the bottom here, those h's cancel. So h is just the distance. H is just the distance between the x's. And then, of course, f of a plus h minus f of a is the distance here between the y. So changing y over changing x, it hasn't really changed, has it? So where do we go from here? Well, pretty simply, we're going to do exactly what the idea we just talked about. We're going to take our h value and we're going to try to decrease it. Okay, so h is going to get smaller, and as h gets smaller, this point gets further back on the curve towards our initial point a, or p. Point p is a, f of a, right? And of course, this makes the y value go down a little bit too. But more importantly, look at that. The secant slope just changed a little bit. It just got a little flatter, didn't it? Well, that's good. That's good because look at the red tangent slope that we're looking for. This slope right here is the slope that only hits the curve at one single point. That's the slope we're after. But once again, I can't find that slope. I can't do y minus y over x minus x if I only have one point. I mean, we know y1 minus y2 over x1 minus x2 is slope. And I could certainly put in f of a for y1 and a for y2, but then we have nothing to subtract if I only have one point. That's the whole point of this, right? So that's why we have to start, like here from I said, with the secant slope. But look what we're doing with that secant slope. We're changing it. We're going to make h a little smaller again. Let's do it. Ready? H just got smaller. Our point just fell a little closer to point P, and the secant slope just got a little bit flatter still. Look at that. Okay, and we're going to keep doing that, and let's see what happens, shall we? How small do we want h to get? How small do we want h to get? I mean, we're getting it pretty close here. But how small? I mean, we want it to be the tangent slope, don't we? If we really want it to become the tangent slope, then we're going to have to push this point all the way back to point P. Which you cannot do with algebra. But which you certainly can do with limits. We're going to take the limit of those secant slopes. Remember, this is the secant slope right here. This is the secant slope, right? Okay. That's the secant slope. Look at it. It's the secant slope. The only difference is that we're not just going to take the secant slope. We're going to take the limit of those secant slopes. It's that h value turns in to 0 as it goes back. Because remember, limits don't care what's actually there. Limits only care what they're approaching. And so I can't find a slope with one point using algebra. I can't subtract a point from itself, I would get 0 over 0, and we know that that's an indeterminate value. But if I take the limit, those secants will get pushed back and evaluate as the tangent slope. And that is called the instantaneous rate of change. That's called the rate of change at a point. That's called the tangent slope, or the slope of the tangent line at a point. And indeed, what you will find out is that's called the derivative. And the derivative is the first major concept you talk about in calculus. In calculus, you really only talk about two big ideas. One of them is derivation. The other one is integration. They are opposites of each other. And when you can connect them as being opposites of each other, which is what Newton did and Leibniz did roughly the same time, way back in the 1700s. That's what calculus is. That's when you've proven calculus. So this picture right here is the idea. The idea of just moving this point back towards this point as h collapses to 0. And what that's going to do is take our secant line and drive it into the tangent line. That is the definition. Look at this animation where the point is moving back from a secant line into a tangent slope. The h value is getting smaller and smaller, isn't it? That's what you keep an eye on right there. As h goes to 0, the secant becomes the tangent. Once again, the secant becomes the tangent. Q is getting pushed back into P. That h value, which I don't label in this one, but starts right at this distance, it's getting smaller and smaller. That's it. The limit, right, as the h value. So they start at here and they move to here. So h starts at about a distance of 1, but it gets tinier and tinier and becomes the tangent slope eventually. This is my favorite because it actually goes really slow. And you can see those secant lines very slowly becoming the tangent line until the points collapse. Bam! The limit of h just hit 0. Could we ever really hit 0? No, we can't hit 0. But that's where our knowledge of limits and how to evaluate them comes into play. Okay? Here's another example here. Instead of h, they're calling it delta x, change in x, which is really what h is. Bam, there it goes. It becomes a tangent. When delta x or h gets to 0, boom, you have your tangent. And one last example here. Look at a plus h getting closer and closer to a until when? Until they converge. And that's when h has approached 0. So algebra is slope. Algebra is y minus y over x minus x. I know this doesn't look like y minus y over x minus x, but remember when we subtracted the x values, the only thing that was left was the difference between the x values, which was h, right? And f of a plus h and f of a are the two y values. So it really is just y minus y over x minus x. When does algebra become calculus? When I take that secant slope, when I take that difference quotient, and I evaluate it as the limit of h approaches 0. That is the difference between algebra and calculus. So now that you are applying what you've learned about limits to the difference quotient, you are officially taking your first step into calculus. Congratulations. Here's a picture of the same situation. Secant slope, tangent slope. What's the difference, right? What's the difference between them? Well, the secant slope is an average rate of change between a and b. There's our f of b minus f of a over b minus a formula. The points are a, f of a, b, f of b. I would have loved if they would have put the difference quotient in here because f of b minus f of a over b minus a is the same thing as f of a plus h minus f of a over h, just with the b turned into an a plus h, right? What happens when we take the limit? Well, we get the tangent line. The slope of the tangent line is what happens when we take the limit. There's that difference quotient. They turn the a that we've been using into a c. Obviously, different books will use slightly different variables. F prime is what you'll learn about in calculus. That means the first derivative. You say f prime is how you read that. The derivative, that's more of a calculus term you'll learn next year. We don't quite get to calling this a derivative, but trust me, it is. This we will call it the instantaneous rate of change, right? We won't really call it that today, But tomorrow we're going to look at some applications when we will definitely be applying that idea. Okay, so have we talked enough about what the difference quotient is? Maybe now it's time to talk about how to apply it, because that, of course, is what we need to do. So here's the first example. In your book, it's all worked out. But for this first one, I'm gonna go ahead and write it out for you. I want you to see this from scratch. Okay. What would a graph of this look like if we actually drew a graph? Well, we know what x squared looks like. X squared is just a happy little parabola. Kind of looks like that ish, right? Except this one is a +1, so it got shifted up 1. Right on. Very, very nice. Now, they want us to find the slope of the parabola at x equals 2. So this is crazy. This is something you've never been asked to do before. Here's 1, here's 2, here's 2. So at x equals 2, there's going to be a slope that just hits the graph at exactly 1 point. That's the slope we want. You could not do that with algebra. There's no way, because this is a single point and you can't find the slope. But luckily, we don't need to, because guess what we've got? That's right, we've got the difference quotient. And so that's what we're going to apply. Now, before we do that, I'm going to do a little work ahead of time. For example, I'm going to figure out what f of a plus h is. Now, some folks, and this is definitely the way that some of the work is in the answer key, because I'll do it this way sometimes. We'll do all of the work within the equation itself. Some people like to do the work off to the side and then plug it in with substitution. You get to choose, okay? Now, our value of a in this value is where they're asking you to find. So this is going to be at 2, okay? So f of 2 plus h minus f of 2 over h. This is actually, this will be the difference quotient right here. This will be the difference quotient. And we don't get the derivative. We don't get the tangent slope until I take the limit, right? I need to take that limit as we approach 0. So let's go ahead and make that minor adjustment. A small bit of writing, but a huge difference in what we're asking. Okay, so the limit as h goes to 0. So this is where some people like to do the work right inside, and they'll plug all of the stuff I'm about to write in. I'm going to do it so it's a little more organized for you. So I'm going to go ahead and write what is f of get off of this because I think I'm on the fade pen. We don't want it to disappear on us. What is f of 2 plus h? Well, that's going to be 2 plus h squared, right? Because I'm plugging it right in here, plus 1, which is going to be 4 plus, don't just square the 2 pieces, please, 4h, right? Because you have to FOIL it, plus h squared plus 1. Or, let's organize it, h squared plus 4h plus 5. I just move the terms around. So there you go. We now know what f of 2 plus h is. F of 2 is just the y value at 2. So that's going to be 2 squared plus 1, or 4 plus 1, which is equal to 5. So these are the 2 things I need to plug in. These are the only 2 things I need to make this difference quotient click. So here we go. Don't stop writing your limit. You got to have that in there. We're not done taking the limit until we've evaluated it. Okay. So f of 2 plus h was h squared plus 4h plus 5. F of 2 was 5. Now, like I said, some people like to write this stuff right here, all this work that I did up here, they like to write it within the difference quotient. So there's no side work, but the work that you're actually doing is much more involved. It's your call as long as you're labeling things and it's organized, okay? What's going to happen? Well, the best thing that's going to happen is that these 5s are going to go away. So now I have h squared plus 4h over h. Notice how everything left only has an h. You see that? If that doesn't happen, if there's still a term in the numerator that doesn't have an h, that has no h, then you made a mistake. You got to go back and find it, because every single time what should happen as you do this process is you should be able to have enough h's in every term to factor one out, which is going to allow you to cancel that with the h on the bottom. Now we're just taking the limit as h goes to 0 of h plus, and I just took that one out, but I didn't not write it. Sorry about that. Plus 4. Okay, the h is in the denominator is gone. That was the problem. That's why I couldn't do this to begin with, and now it's gone. So now I can just substitute the h in. Notice I'm going to stop writing the limit now because I'm evaluating it. And 0 plus 4, of course, is 4. We just found the slope of this line right here. Okay, at 2. Now notice there's a lot of different slopes. Slope could be 0 for the vertex, it's horizontal, right? It could be negative on this side, negative slopes. And the slopes are only going to get steeper the further out we go, because the parabola gets steeper, the slopes of the curve get steeper. But at this point they asked us about, the slope is 2. Or I'm sorry, at 2 the slope is 4, and that's it. You just found it. And it's a process that once you do it 4 or 5 times, you start to catch on, and then it's really not that bad. Okay, so like I said, this was already worked out in your course pack, and as you can see, we did evaluate f of 2 plus h off to the side. We did evaluate f of 2. Those are the exact same values you see. We made the substitutions. The 5's disappeared. We factored the h. We substituted in the 0, and we get a slope of 4. Now the second part of this becomes very simple. The second part of this just says, what's the equation of that tangent line? Well, we have the slope, and you actually already found the point. The x value they gave you, the x value was 2, and the y value you solved for right here, right? F of 2, you found it was 5. So yeah, you already have the point. It's the 0.25. And so here's your slope, your point. We plug them into mx plus b, or I guess you could use point slope if you really wanted to, but it's pretty simple to solve for the intercept by just plugging in and simplifying, solving for b, and then there's your final equation at the bottom there, 4x minus 3, the tangent slope with the correct intercept. Here's a little picture of this graph for you. This one was actually, I think, not on the calculator, but on a computer generated image. But you can see that tangent slope. I just plugged in the line, I plugged in the curve, and you can see that perfect tangent relationship that you found. Okay, so let's talk about one more thing. It's a definition. It's called the normal to the curve, and it's defined as the line that is perpendicular, okay, to the curve at, and it's perpendicular not to the curve itself, but to the tangent at the point of tangency. So you can't be perpendicular to the curve because the curve is curving, but if I have a tangent line, I can definitely be perpendicular to that line. So the main thing you have to remember here is something you learned back in Algebra 1/geometry. We reviewed it earlier this semester. Perpendicular slopes. Perpendicular slopes are opposite reciprocal slopes. Okay, so here's an example from Algebra 1 where we have, up 4/3, we have down 3/4, positive 4/3, negative 3/4 create that perpendicular relationship. So this next problem that we're going to see here is going to be very similar to the first one. This time it's a negative parabola for minus x squared, and they want us to find the tangent slope at 1. Okay, so we're going to write the equation of the tangent line and then the normal line. So they added one part here, part C. Okay, but let's go through the main work. I mean, once you get done with part A, this is Algebra 1 work here. This is nothing. Okay, all you need to do is get through that first part. You get through part A, which is the calculus part. Your money. You're in good shape. So we're going to go ahead and find f of 1 plus h. Remember, this time A is equal to 1. They tell us, what they want A to be on these problems. So A is 1. So I'm going to go ahead and plug 1 in for A, and I'm going to reduce my equation. So 4 minus x is going to be 1 plus h. So I plug 1 plus h in for x. I have to FOIL that. Don't lose your parentheses. That's a big mistake because people lose that minus and they only have the first term negative and not the other ones. You have to distribute that negative all the way through. So because all three of these terms in this trinomial are positive, after I subtract them, now they're all negative. Don't forget to follow algebra. And then it reduces to 3 minus 2h minus h squared. That's my parabola. What we're going to do now is we're going to find f of 1. Well, that's a little bit simpler. No variables, just plug a 1 in. 4 minus 1 is 3. So I've got f of h, or f of 1 plus h. I've got f of 1. It is now time to substitute into the difference quotient. One big mistake I see a lot with people when they're first learning the difference quotient for the first time, I see a lot of still writing x goes to 0 because you're so used to it from earlier in this unit, and even through continuity, we're always talking about x going to 0, x going to c, x going to this. Well, we're not worried about the x values. We're not approaching x values anymore. Now h is always approaching 0. The difference quotient wants the distance between points to go to 0. So it's not about x values anymore. It's actually about the distance between x values, which we call h. So do be careful about that. So this first step is just taking the things I found up here and putting them in. Everything without an h better go away. It does. 3 and a negative 3 cancel. Notice all I have left are things with h's. I factor the h out of the top. The h cancels. Look at that. Negative 2 minus h. I can substitute anything I want into that. I put the 0 in, and I get an answer of negative 2. So there's the hard part. But if you really follow the steps, other than the numbers being slightly different, it's exactly the same as example 1. So you're just going to have to work at this and do it until it starts to click. And if it's not clicking, come get some help from me, all right? All right, part B, find that tangent line. Well, we already found the point. The point that gave us the x was 1. We found the y was 3, so the point is 1, 3. And we just found that the tangent slope was negative 2. So now I just have to put those into y equals mx plus b. And after like 2 steps of reducing and solving, simplifying and solving, I get my tangent line. The normal line, we're going to use the same point because the normal line goes through the point of tangency. So I use the same exact point, but I have to take the opposite reciprocal or negative reciprocal of negative 2, which is positive 1/2. And then I just go through the process again. This time I get a b value of 5/2 or 2.5. And there you go. Okay. Like I said, parts B and C are really Algebra 1 stuff. Part A, that's the one you really want to practice a lot tonight. So that's going to basically do problems 9 through 14 for you. Most of them are polynomials, but they're very similar to that concept. Problems 15 through 18 are a little different. You're doing the first 2 of those, and it wants you to check for tangent slopes coming in from each side. And this is what has to occur for tangent lines to exist. And in calculus, you say, is it differentiable? Is there a derivative? Is it differentiable? 2 things have to happen for a function to be differentiable at a certain point. For us, we're saying 2 things have to happen for a tangent slope to exist at a point. First of all, the function must be continuous at that point. If it's not continuous, which would mean any type of discontinuity, you cannot have a tangent slope existing there. It has to be continuous. That's why calculus loves continuous functions more than anything, okay? Which is why we just studied it for a whole week last week. Also, tangent slopes have to agree coming in from each part of the function. Notice these are piecewise functions, so you have a left half and a right half. Well, they've got to agree. Even if it's continuous, if the tangent slope doesn't agree, then it's not going to work, okay? And so this is how we would write that. The limit as the distance between from the left, so the x's the points are approaching each other from the left side, that's what that little negative is right there, has to be the same as if we take the limit of the secant slope or the difference quotient from the right. Okay, so let's check out when you can't have a tangent slope. Any type of discontinuity is going to be a real problem. You don't really have to worry about the old oscillating discontinuity, but we definitely just reviewed all of these really well, didn't we? And then these we're not going to really talk about in this class very much. You might see a couple in examples, but this one they call it a kink. I think officially most books call it a corner, and it happens anytime you have an absolute function or piecewise function where you have a really sharp point. Or an even sharper point would be where you have two curves, one of them decreasing, one of them increasing, and they meet at a point at the bottom or the top, and it creates a really sharp, even sharper than a corner. That's called a cusp. And the problem with these is at the point of intersection of the two different directions, the tangent slopes will not agree. The easiest way to see that is with the absolute value function, because these tangent slopes are going to just match the slope of that negative line. So if that's a -1, that's a slope of -1. But on the other side, the slopes are +1. And so even though this function is continuous here, the tangent slopes are not agreeing with each other as you approach that point in each direction. So you can't have differentiability when you have abrupt changes in direction is basically what I'm trying to say here, okay? So here is kind of how you would go through one of these. I'll just work, say, number 15 out for you, and then we'll call it a day, all right? Let's start with the left half of the function. So we're going to take the limit as h approaches 0 from, oops, I guess I need to get off of the magic pen, just get to a normal pen. So the limit as h approaches 0 from the left of, so we're going to use this function right here. The nice thing is that I'm just doing 0. So that means that f of a plus h, right? F of a plus h is just going to be f of 0 plus h, or f of h. So I can just do for f of a plus h, 2 minus 2h minus h squared. And what happens if I put a 0 in? I get 2 minus 0 minus 0, right? So that's just going to be a 2. So this is f of a plus h right here. To f of 0 plus h specifically, this is just f of 0. And it's all over h, right? So what's going to happen on top? Well, hopefully we see some stuff going away, like the stuff that doesn't have the h values. So now I can factor out the h, leaving me with -2 minus h on top, which cancels. And you're going to see this, very similar almost all the time, what's happening. Expand stuff, simplify stuff, stuff without h's better go away, and then you can substitute in. It's very, very similar how these all work out. There's your slope from the left. Now, what about the slope from the right? All right. So same idea, except I'm going to have to use the other side of the function, the left side of 0. So limit h approaches 0 from the left, or from the right, I should say. So this time, when I put a 0 plus h in, which is just 0, or I'm sorry, just h, right? 0 plus h is h. I'm going to get 2 times h plus 2 for f of h. So 2h plus 2 minus, and then when I put a 0 in, I'm just going to get a 2, right? 2 times 0 is 0 plus 2 is 2. So this is f of 0 plus h, this is f of 0, all over h. Does everything on the top that doesn't have a 0 cancel out? I bet it does. 2 minus 2, gone. All I have left is 2h over h. The h is canceled. We know that the limit of a constant, right, is always itself. So check this out. +2 is the tangent coming from the left, or I'm sorry, from the right. -2 is the tangent coming from the left. Is -2 equal to 2? And of course, the answer is no. And so your answer for number 15 would be that no, the slopes don't work. Now, the first thing you really should do on this, because it's a simpler thing, is I would check continuity. So maybe just plug a 0 in and make sure it's a continuous function. In this case, it would have been, because if I plug a 0 in the top, I get a 2. If I plug a 0 in the bottom, I get a 2. Number 16, if I plug a 0 in the top, I get a 0. If I plug a 0 in the bottom, I get a 0. So continuity, check first. Check continuity first. Then you can move on and check the tangent slopes coming in from each side. So big day, huge day, massive day. The rest of this packet, I'm going to break into 2 sections. Okay, so 9 through 16 is going to give you some generic problems and just a couple of the problems like we just did. And I just did one of them for you. I just did 15. So just try number 16 and see how that goes. And then, you know, you can get excited for tomorrow, in which we we'll use some of this stuff to apply to applications. 17 and 18 are kind of like the last 2 I just showed you, but 23 through 30 are where we actually see how this stuff starts applying to real world situations. So I hope this was followable in a you know, remote learning. This is one lesson I would never want to do remotely, but we don't have a choice. So good luck. Let me know how I can help you, and we'll talk to you soon.